Hello, I'm Rob Campbell from practicalprecision.com, where we help clients and engineers, perhaps like yourself, to develop products that depend on precision motion and precision optics for success through directly consulting with them, providing design tools, and also from professional development like this series of videos. I'd like to welcome you to day one of the Inktober challenge that I'm taking. Inktober was actually started by a cartoonist, Parker, as just a way to kind of get back in touch with the joy of drawing, the freedom, just improve his skills by producing one ink drawing every day in October. It's kind of taken off, and I've always drawn, and it's always been actually a powerful skill, I believe, that I've brought to engineering through my professional career as working for companies and now as a consultant. I really think that engineers should brush up on that capability. It's a powerful tool for communicating that you understand something and for exploring ideas. And we can be too reliant on CAD tools and other things like that, which are wonderful, but just for this quick and dirty, nothing beats being able to produce a reasonable drawing or diagram on a whiteboard, a sheet of paper. And so that's hence this video. Just going to go through this for 31 days of October. I haven't really thought it through too much. I guess in general I'm going to take the approach of that I would with a consulting client. Kind of go in and imagine that we're starting from almost from scratch and trying to develop that understanding of what the client wants to build and what their goal is for it, and then to identify the challenges that we need to consider in it, and then we'll take that design as far as it go. We'll go through 31 days of whiteboard drawings and other. For me, for now, right now, that's it. Just me and a whiteboard, no script, no plan. So we'll see how this gets off to, kind of start we get off to. All right, I'm going to start with a little bit of background and maybe education. I'm going to define precision engineering, what it means to us at Practical Precision. And precision engineering is the art and science of designing something that will move, measure, or make something with a level of accuracy that is much smaller. In this case, accuracy is a good thing, than the size of the thing itself. So if you're producing a part on a CNC tool to within microns, if you're measuring something to within microns, one of the things that I want to point out, this move, actually, I'm going to say move or hold. So when we're dealing with optics and optomechanics, the field of optomechanics, often we're not moving something. Sometimes we are. But a big part of optics from the mechanical engineer's point of view is to hold the optical element in the ideal position in space without it moving significantly such that it degrades optical performance throughout the environment that it's exposed to. But it turns out that the principles that allow you to move something very precisely, many of them are the same principles that allow you to hold something very precisely. So precision machine design and optomechanical engineering I consider as two sub-disciplines of precision machine design. They're very closely related. So, and again, it's the accuracy is much smaller than the size of the thing itself. That's kind of a relative term. It's a sliding scale. If you're doing we do some very large printing systems, and we're not getting to the sub-micron level there, but we are moving things around with quite a bit of mass quite rapidly in order to either print or cut a pattern very accurately relative to the size that it's viewed and the size of the machine. So there's a lot of elasticity in that machine that makes it difficult to produce an accurate pattern at a high speed. And again, it's the same principles that we use to design a a wafer bonder for the semiconductor manufacturing industry that needs to hold accuracy on the order of microns, a single micron. The same principles apply. So again, that's my working definition of precision engineering. Now, as I mentioned, we're going to take this approach, imagining that I've come into a conference with a client, and I will know a little bit going in. I'll get the call, and I'll do research. So I'm never going in cold, but the goal is to really understand both the technical as well as the strategic requirements for the product. And oftentimes, to be honest, it's to help the client formulate those in a precise meaning, or in a way that we can actually act on. Translate their general terms. They're often very prescriptive, such as we need a stiffer beam, a beam that doesn't bend. And really, it's not the beam that they're looking for. They're looking for an overall system stiffness that will allow them to move more quickly and achieve their accuracy levels with that faster throughput. And a stiffer beam might be part of it, but only a small part. If you really go ahead and start just take them at their word and start designing a stiffer beam, you're not doing them a good service. You may well do that and not meet their end requirement. So you really need to start that initial meeting as kind of exploratory. And this applies to as well if you're an engineer at a company. As you're defining that problem, you start at a high level and you try to translate a collection of requirements of various sources into something that really defines the performance of the machine. At Practical Precision, we have a formal process for that. We call it Precision Foundation. And the first two steps of that we'll start Inktober off with is to define success and performance. For both the machine as well as the product. And the second step will be to visualize the solution. Some people have a very, very formal product development approach where if you were to jump to this step too early to visualize, they see it as really getting ahead of the requirements. But the reality is that it's hard to talk about things purely in hypotheticals. So very early on, you're going to be standing in front of a whiteboard like this and you're going to be sketching. So that's what visualizing is. In terms of performance for a precision machine, it's important to define with the client what that means. And again, in terms of precision engineering, performance is typically defined in terms of some level of accuracy. And again, so if you're producing something, you're making something, a CNC machine, then accuracy would be defined as the deviation between the perfect form of the thing that you're trying to produce in the actual form. If it's a coordinate measuring machine, then the accuracy would be the deviation between the measurement and what the actual thing were, if you could know that with perfect certainty. Precision motion, often it's just following an intended path. So again, accuracy will depend, as we mentioned before, and it varies, but it's accuracy in terms of constraints. So this might be very often throughput. You want to produce a certain number of these items. And then also, and that's all subject to within environment. Typically the environment comes into play as the third part of performance, such as it needs to be able to operate in the desert, if we're talking about an imaging system for a long-range targeting system. So that can be both the external environment as well as the internal environment. A lot of tools with special processes, such as what we'll be looking at, additive manufacturing, additive metal manufacturing, or wafer bonding, involve extreme heat. So there are internally created environmental conditions that we need to consider, and sometimes it's the external technically the environment is just another constraint, but it really makes sense to frame it in this way where there are external considerations. So that's what our performance is. We need to define with the client what the performance, the constraint is often what ties it to their end user. You know, how is it viable in the marketplace, such as throughput. In this scenario, starting off with Inktober, let's just say we're going to do, it's a client has contacted us about 3D additive metal manufacturing, so on an industrial scale. So we're really taking, for hundreds of parts, the goal is hundreds of parts per run with a high level of accuracy, significant complexity, and materials, metal materials as opposed to your hobby shop plastic type 3D additive manufacturing. It's technology. It really is transforming manufacturing. Will have a big impact coming forward. So 3D additive manufacturing process that uses metals, and we'll describe what that process is and that it was communicated to us. And then the added wrinkle will be, so we have this 3D additive manufacturing, and we want to bring that and make that part of a larger manufacturing process. So there's this notion of palletized production. So in CNC machining, you often, on these highly automated systems, you'll have a pallet which has some kind of features, often kinematic mounts, and you will just strap a billet of aluminum to it. And you might have 20 of those, and it will move through multiple machining centers and different processing centers. So what we're looking to do is mimic this scenario, but for 3D additive manufacturing and the challenges that it brings. Typically these are going to be done at room temperature, but as we describe the process for the 3D additive manufacturing, we'll see that there are other challenges that we need to consider. And in designing anything really, I tend to work from what I call the product outward, and the product is variable. In some cases in manufacturing, CNC or 3D additive manufacturing is literally the product that you're building. In semiconductor processing, it may be a wafer that's going from stage to stage, and you're building up the devices on that. But you'd want to build from the smallest, thing of significance outward, which might be the wafer, or in a wafer bonder, it's the wafers that need to be aligned to each other. Some cases it's the patient. It's literally, if it's a medical device, it is designing from the interface, the patient interface, outward. So in this case, product is really some blob or some profile with a complex shape. And in this process, it may be, and in particular, one of the advantages of the 3D printing is it may have features that are not readily manufacturable. So here we've got some kind of, this is just absurd, but some kind of pipe that comes around here, wraps around and connects on the backside there, various protrusions, looks like a tea kettle, but something like this that would not necessarily be feasible for manufacturing. It may have swept surfaces, just something like that. So the way that these are often produced, and in the particular technology that we're looking at now, and there are machines like this, and this would be a variation on it, as opposed to coming in and machining it, this is produced in layers. And it's built up, and with those layers are fine enough, then you can achieve the level of accuracy that's required. And in this case, we're looking again at a metal process, so it's essentially we're going to be melting layers of metal and solidifying those. So we also get a very high, it's a solid structure suitable to industrial applications when all is said and done. So again, in this scenario, then, if you imagine as we're building up, I guess a little bit word about the process. This is going to be produced in a vacuum chamber. So this would chamber of some kind. And the way that it works, we're going to wipe this guy out for now. Then we'll have a bed here. And as we go down through it, it'll actually be, if you think of it perhaps as a piston. Piston, which can move up and down inside this chamber. The chamber would be evacuated to clean it and then probably backfilled with argon or another noble gas. There would be a layer of powder, a powdered metal that's brushed across here. So what we would do is we would lower this, say, so it's thousandths of an inch or whatever the minimum thickness size would be. We would lower that and then kind of backfill our powder across that surface. And we would have an optical system up here outside of the chamber. And so we'd have some kind of scanning system. And maybe 2 mirrors, 2 galvo mirrors. But we would have a high power laser sitting up here. Perhaps going through various conditioning optics and then hitting 2 steering mirrors, which will allow us at a distance to draw a pattern in that powder. Perhaps there were 2 different galvos here, perhaps there's an XY, but speed is going to be paramount. So that's as we think about that, throughput is key, especially in an industrial manufacturing. So that has to be a high-speed scanning system, not necessarily only, but it does suggest some galvos. So we're removing some very small masses very quickly in order to scan that platform. In any event, so we have scraped on a layer of our powder. This needs to be heated by quite a bit. So T is high. Let's see, T sub P, we'll call it the platen. So we need to introduce heat into that. As we know, heat causes distortion. In general, you want to let a machine like this athermalize so that everything's at a uniform temperature as much as possible. There's certainly some wrinkles that we'll get into regarding that, but we're going to have to heat that plate, let platen, to hundreds of degrees Celsius. We're close to it to help with this process, and then the laser will do the melting. So that'll be a consideration that we look to as well. So that's our basic setup. So as we lower this, we can build up layer by layer by layer.